All right, let's take a look at our first example of surface area. The directions are to find the surface area of the solid shell generated by rotating the arc of the parabola y equals x squared from the point 1, to the point 2, about, in part A, the x-axis, and in part B, around the y-axis. So in both cases, we're talking about the point 1 and the point 2, and that bit of arc along the parabola y equals x squared, 1, 2, 4. And in the first case, we're talking about We're talking about rotating about the x-axis versus rotating about the y-axis. And they generate some pretty different shell shapes. And by shell, I just mean that we're not talking about the volume. This is like your favorite candy coating shell around whatever geometry you're into. So I want to look at the two differences here because they are quite different. There's a couple of different ways that we can do B. A is pretty straightforward, though. Part A here is just around the x-axis, so let's just start with the general surface area formula with respect to the variable x. We have the integral from, I should say, x equals A to x equals B of 2 pi times the radius as a function of x times the square root of 1 plus f prime of x quantity squared dx. So actually, let's move this wonderful drawing out of the way here. We'll do this guy later. There's a lot going on with that one. Let's move this up top here. There we go. So with respect to x, we have the surface area is equal to this formula. In this particular case, that's the integral from x equals 1 to x equals 2. 2 pi, and the first thing that we need to talk about here is what our radius is going to be. Now, the radius is always measured from the axis of rotation to your curve. Whether you're talking about volume or any other kind of rotation that we've done in this course, it's measured from the axis of rotation up to the curve. So let's get that on the board here. Here's the axis of rotation. And we want the distance up to the curve. That is going to be our radius as a function of x. And in this particular case, it does look like it's just the function f of x, or in this case, x squared. So that's pretty easy to do. So this will be x squared. Then, what do we have here? For f prime of x, and setting up the rest of this, oops, let's get black here. We have the square root of 1 plus the derivative of f of x is just 2x quantity squared dx. And there's our setup. So this was, in this case, f of x, and this was f prime of x. Okay, and that's going to be equal to, if we factor out the 2 pi, the integral from 1 to 2 of x squared times the square root of 1 plus 4x squared dx. And there's the setup. And this particular problem is probably best done with a trig substitution. So let's do that. Probably going to need some more room down here. Come on. Let's get you out of the way, just in case. Stay safe, buddy. Okay. So let's go ahead and, what do we got here? Looks like we got a tangent substitution. I am going to let's see, this is a squared plus w squared, where a is 1 and w is 2x. So in general, we need to let w equal a tangent of theta. And so my choice here will be 2x is equal to the tangent of theta. So that 4x squared will equal tangent squared theta, and 2 dx is equal to secant squared theta d theta. It looks like we got some mean secants coming our way. Ooh, secant to the 5th is not going to look friendly. Let's see here. So this is then going to become 2 pi. Maybe we're not going to get a secant to the 5th. This is x equals 1 to x equals 2 of, let's see, if 2x is equal to tangent of theta, then x is equal to 1/2 the tangent of theta squared times the square root of 1 plus tangent squared theta, and then dx is secant squared theta over 2 d theta. And we're going to get 2 pi over, let's see here, this is a 1/2 squared, which is a 4th, and another 2 in the denominator is going to put this over 8. The integral from x equals 1 to x equals 2 of tangent squared theta, the square root of secant squared theta, times secant squared theta d theta. And it looks like we're going to get pi over 4 times the integral from x equals 1 to x equals 2 of tangent squared theta secant cubed theta d theta. So kind of a rough first example. What we're going to do is we're going to rewrite this as pi over 4 times the integral from x equals 1 to x equals 2 of secant squared theta minus 1 times secant cubed theta d theta. That's pretty standard, and then we can multiply that out. Pi over 4, x equals 1, x equals 2. Secant to the 5th, yikes, d theta, secant to the 5th minus secant cubed. And hopefully we all know how to integrate secant cubed at this point. So what we're going to do then is we're going to break this up aside. Let's do this. We know that the integral of secant cubed theta is 1/2 secant theta tangent theta plus the natural log of the absolute value of secant theta plus tangent theta. That is a double cyclic integral, and we've done that one a few times in this course. But we haven't done secant to the 5th, I don't think. And it's not going to surprise you probably how we do this if you're fairly well versed in secants and tangents. This is the integral of secant cubed times secant squared theta d theta, and we're going to use some integration by parts here. We're going to use integration by parts because we have absolutely no problem integrating secant squared d theta. That's a piece of cake. And we shouldn't have any problem differentiating secant cubed. So du here is 3 secant squared theta times the derivative of secant, which is secant theta tangent theta d theta. Let's move that out of the way. And v is going to be the tangent of theta. If you're a little lost here, I used the chain rule. I really treated this as the secant of theta cubed. And then if we clean this up a little bit, this is 3 secant cubed theta tangent theta. Let's make that look like an actual cube. And v is tangent of theta. So this will become uv secant cubed theta tangent of theta minus 3 times the integral of secant cubed theta tangent squared theta d theta. And probably no surprise here that if we rewrite that again using a Pythagorean identity, this is secant cubed theta times secant squared theta minus 1 d theta. Kind of running out of room here. Let me push some of this off to the side, folks. Come on, just a little bit more room. You're probably going to have to move again. Sorry, buddy. It's okay. You've been bumped. Multiplying that out, that is secant cubed theta times the tangent of theta minus 3, the integral of secant to the 5th theta minus secant cubed theta d theta. And if we break that up, this is secant cubed theta tangent theta minus 3 times the integral of secant to the 5th theta d theta plus 3 times the integral of secant cubed, which we know is 3 times 1/2 the secant theta plus tangent theta plus 3 times 1/2 the natural log of the absolute value of the secant of theta plus the tangent of theta. Yikes, this problem's a nightmare. Plus C. But what we did get to happen was we got the secant 5th to the theta integral to pop up again. So this is double cyclic. We'll add that over to the other side. And what we're going to see is 4 secant to the 5th theta d theta is equal to secant cubed theta tangent theta plus 3/2 secant theta tangent theta plus 3/2 the natural log of the absolute value of the secant of theta plus the tangent of theta. Oh, my handwriting's getting sloppy. Just get this over with. Plus C, and then we'll divide both sides by 4, and we'll know what the secant of the 5th is. So what were we working on? Remember, we were trying to do this integral. Let's see here. So duplicate. Let's bring this all the way down here. And so this is going to be equal to pi over 4 times the quantity, the integral of secant to the 5th, which is 1/4. Well, we actually, let's combine like terms here. We're going to have to in a second. Let's see, 1/4 secant cubed theta tangent theta plus 3/8 secant theta tangent theta plus 3/8 natural log of the absolute value of the secant of theta plus the tangent of theta minus the integral of secant cubed, which is 1/2 secant theta tangent theta. Running out of room again. Will it ever be over? No. Minus 1/2 the natural log of the absolute value of the secant of theta plus the tangent of theta. Ugh. Evaluated. Between x equals 1 and x equals 2. How many times is this other one going to get bumped? Gee whiz. Okay, so let's collect some like terms here and clean this up. This is pi over 4. Let's just multiply that out. Pi over 16 secant cubed tangent theta. Plus, let's see, we have a few secant theta tangent thetas. So 3/8 minus 1/2 is 3/8 minus 4/8 is negative 1/8 times pi over 4 is negative pi over 32 secant theta tangent theta, I hope. And similarly, we'll have, what do we got here? 3/8 natural log of the absolute value minus 1/2 the natural log of the absolute value. And that's going to also give us negative 1/8 times pi over 4 is negative pi over 32 natural log of the absolute value of the secant of theta plus the tangent of theta. Evaluated from x equals 1 to x equals 2. And now we can undo our trig substitution. Looks like I left out a theta there. Our original substitution was 2x was equal to the tangent of theta. So drawing a little reference triangle here, theta, the tangent is opposite over adjacent. This is 2x to 1, and this is the square root of 1 plus 4x squared. And so this is equal to pi over 16 times the secant, which is hypotenuse over adjacent cubed, is going to be 1 plus 4x squared to the 3/2 times the tangent, which is 2x, minus pi over 32 times the secant, 1 plus 4x squared into the radical times the tangent, which is 2x, minus pi over 32 times the natural log of the absolute value of the secant, square root of 1 plus 4x squared plus the tangent 2x, from x equals 1 to x equals 2. Let's plug some of that garbage in, shall we? Let's see, when we plug in 2, we're going to get pi over 16. 2 squared is 4 times 4 is 16. 17 to the 3/2 power times 4 minus pi over 32 times the square root of 17 times 4 minus pi over 32 times the natural log of the square root of 17 plus 4, which could be cleaned up a little bit, but come on now. Minus, when we plug in 1, we get nothing. We still get nothing nice. Pi over 16, 5 to the 3/2 times 2, minus pi over 32 times the square root of 5 times 2, minus pi over 32 times the natural log of the square root of 5 plus 2. And I'm not going to do any more to that. That was ridiculous. That was a bad first example, and I should have really sheltered you from that. But they're not always going to be that hard, and I don't think that that's a good quiz or exam problem. Man, that was nuts.